Good day! I am Denise Burgos and I'm going to talk about spread spectrum. Spread spectrum is a modulation technique used for transmitting radio or telecommunication signal in which the transmitted bandwidth is larger than the information signal bandwidth. Obviously, the bit rate of the spreading sequence is much higher than the input data. For example, there is an input bandwidth signal as B that would pass through the spread spectrum or spreading process. Then, it would produce a new bandwidth which is much larger than the input signal and is called as the corresponding spread spectrum signal bandwidth or BSS. As we can see in the figure, the spread spectrum increases the bandwidth of the input signal by a factor n, which is called as the processing gain or spreading factor. N equals BSS over B, where B is the input signal bandwidth and BSS is the corresponding spread spectrum signal bandwidth. Block diagram of spread spectrum. First, the input data is fed into a channel encoder that produces an analog signal with a relatively narrow bandwidth around some center frequency. Then, the signal would be modulated further in the modulator or spreader using a coded sequence of ones and zeros with certain autocorrelation properties called as pseudo-noise coding sequence that is generated by a pseudo-noise generator or deterministic algorithm. This noise is a maximum length sequence, which is a type of cyclic code, and only the receiver can decode the signal since it is required to know the algorithm and seed to predict the sequence. The effect of this modulation is to significantly increase the bandwidth or spread the spectrum of the signal to be transmitted. On the receiving end, the same digit sequence is used to demodulate the spread spectrum signal in the demodulator or the spreader. Lastly, the signal is fed into a channel decoder to recover the data. Advantages of spread spectrum. By transmitting over a larger bandwidth, the robustness or the quality of being in good condition against the external interference is increased. Since the wider the bandwidth of a transmitted signal, the lower the influence of interference over a small part of the bandwidth. This is the main advantage of a spread spectrum technique, which would make the signals modulated hard to interfere and its resistance to jamming. Hence, these techniques are used for military purposes and was adopted more recently in commercial wireless communications. The other advantages of the spread spectrum are high processing gain, noise reduction, easy encryption, greater security, and multiple access. Spread spectrum multiple access techniques uses signals that have a transmission bandwidth of a magnitude greater than the minimum required RF bandwidth. The two types are frequency hopping spread spectrum or FHSS and direct sequence spread spectrum or DSSS. Frequency hopping spread spectrum. Frequency hopping spread spectrum or FHSS transmission is the repeated switching of frequencies during radio transmission where the transmitter hops in a random but predictable sequence from frequency to frequency as a function of time over a wide band of frequencies which is already known to the sender and receiver. For example, a frequency was allotted to sender 1 for a particular period of time. After a while, sender 1 hops to the other frequency and sender 2 uses the first frequency, which was previously used by sender 1. This is called as frequency reuse. The receiver also hops between frequencies in sync with the sender. The frequencies of the data are hopped from one to another in order to provide a secure transmission where the eavesdroppers hear unintelligible blips. The amount of time spent on each frequency hop is called as dwell time. As seen in the figure A, the transmitted signal is spread across multiple channels. The full bandwidth is divided into 8 channels centered at F1 to F8. The x-axis is the frequency, while the y-axis is the energy used. The numbers above are the sequence from which the signal would hop from frequency to frequency. In the next figure, x-axis as the time and frequency in y-axis. The signal hops between them in the following sequence: F5, F8, F3, F7, F1, F4, F6, and then F2. Block diagram of HSS transmitter. In the diagram, the non-return to zero data, or simply the binary data, are fed into a modulator using digital to analog scheme like frequency shift keying or binary phase shift keying for effective coherent detection. The resulting signal is centered on some base frequency. A pseudo-noise source serves as an index into a table of frequencies. This is the spreading code. Each k bits of the PN source specifies one of the 2 raised to k carrier frequencies. In the figure, there is a 3-bit code in the pseudo-random number source, therefore, the total combination is 8. At each successive interval, a new carrier frequency is selected. For example, 101 has a carrier frequency of 700 kHz. Therefore, this carrier frequency is modulated by the signal produced from the initial modulator to produce a new signal with the same shape but now centered on the selected carrier frequency. After 8 hoppings, the pattern repeats, starting from 101 again. A bandpass filter is used to block the difference frequency and pass the sum frequency, yielding the final FHSS signal as S of t. Block diagram of FHSS receiver. The spread spectrum signal is demodulated using the same sequence of PN-derived frequencies and then modulated to produce the output data. At the receiver, a signal of the form S of t will be received. This is then multiplied by a replica of the spreading signal to yield a product signal. Again, a bandpass filter is used to block the sum frequency and pass the difference frequency, which is then demodulated using FSK or PSK to recover the binary data. Direct sequence spread spectrum. Using DSSS, each and every bit of the user data is multiplied by a secret code, called as the chipping code. This is a transmission technology where a data signal at the sending station is combined with a high data rate bit sequence, which divides user data based on a spreading ratio, which results in a wideband time continuous scrambled signal. The spread is in direct proportion to the number of bits used. One method used in DSSS is to combine the digital information stream with the spreading code bit stream using an exclusive OR. Note that an information bit of 1 inverts the spreading code bits in the combination, while an information bit of 0 causes the spreading code bits to be transmitted without inversion. The combination bit stream has the data rate of original spreading code sequence so that it has a wider bandwidth than the information stream. The data rate is equal to the original spreading code. As seen in the figure, the spreading code bit stream is clocked at 4 times the information rate. When the data input A is at 0, the spreading code bits was transmitted without inversion since the transmitted signal was same with the generated bit stream. When the data input is at 1, the generated bit stream was inverted, thus the transmitted signal is different. Block diagram of DSSS transmitter. The binary data is fed to the modulator using a BPSK modulation scheme. The binary data is represented with a positive 1 and negative 1 rather than 1 and 0. In order to produce the DSSS signal, BPSK signal is multiplied to the PN sequence C of t, taking on values of positive 1 and negative 1. A chip generator can be added after the PN bit source in order to define the bandwidth offered. Block diagram of DSSS receiver. At the receiver, the incoming signal is multiplied again to the PN sequence where C of t times C of t equals 1. Therefore, the original signal is recovered. Then, the signal is demodulated to recover the original binary data. The second method is the discussed method using the BPSK scheme as shown in the figure. Approximate spectrum. The information signal has a bit width of t, which is equivalent to a data rate of 1 over t. In this case, the spectrum of the signal, depending on the encoding technique, is roughly 2 over t. Similarly, the spectrum of the PN signal is 2 over t. The amount of spreading that is achieved is a direct result of the data rate of the PN stream. Code Division Multiple Access. CDMA is a digital cellular network standard and a multiplexing technique that utilizes spread spectrum technology. This technology does not constrict bandwidths, digital signals, or frequencies, but spreads it over a fully available spectrum or across multiple channels via division. Thus, there is improved voice and data communication capability and a more secure and private line. Given a data signal rate D, each bit into K chips according to a fixed chipping code specific to each user. The resulting U channel has a chip data rate of KD chips per second. This technique can also have a multiple channels superimposed.